The Columbia River Gorge showcases some of the Northwest's most astounding geology. From Cascade volcanoes that erupted 30 million years ago and still continue today, to Ice Age floods that swept through the landscape only 15,000 years ago, this is a place that records the history of the Northwest. We're going to focus on the Columbia River basalts, lava flows that blanketed the Northwest and form most of the walls of the gorge. Some of the gorge's most important geology is found in the dark brown lava flows that form these walls. These rocks are basalts. They were once torrid, fast-moving lava flows that erupted from fissures in eastern Oregon, eastern Washington, and even Idaho, and flowed all the way to the Pacific. They're some of the longest and most extensive lava flows on the planet, and geologists today are still studying them. Here in the gorge, these basalt flows are named after the river that exposes them so well. Collectively, they're called the Columbia River basalts. And almost every layer in the gorge walls is a different basalt flow. Here at the Rowena Plateau, you can see behind me a great thickness of Columbia River basalts, about 1,000 feet of basalt flows altogether. Columbia River basalts erupted for about 10 million years total, from 17 million years ago until about 6 million years ago. These basalt flows produced enough basaltic lava to build a road from the Earth to the moon, a 1/4 mile wide and 100 feet thick. Put another way, that's 63,000 cubic miles of basalt. Now, this didn't happen all at once. These flows erupted in 4 discrete episodes. The oldest are called the Imnaha. The next are the Grand Ronde basalts that are the most voluminous. Then there's the Wanapum basalts that are found really around the Dalles and sort of central Washington. And finally, the Saddle Mountains basalts, which are the last squeezings of the basalt flows, but also include the longest basalt flow on the planet. So the Columbia River basalts are a great example of a large igneous province, what geologists would call a lip. And behind me at Rowena, you see an excellent example of why they're such a world-renowned igneous province. The Columbia River basalts and related basalt formations cover much of eastern Oregon and Washington. Geologists now divide them into 2 major groups. The Steens Basalts, found near Steens Mountain in southeast Oregon, and the Columbia River basalts, which cover most of the Columbia River Plateau. The earliest of these flood basalts, or large igneous province basalts, are called the Steens Basalts. They erupted near Steens Mountain about 17 million years ago. These eruptions marked the beginning of the Yellowstone hotspot, the same source of lava that today powers Yellowstone National Park and Yellowstone Caldera, as well as marking the inception of Columbia River basalt volcanism. Then, about 16.7 million years ago, the major basalt eruptions shifted north, producing the Columbia River basalts. These voluminous lavas cover most of eastern Washington and east central Oregon, including the Columbia River Gorge, and they go all the way to the coast. The Columbia River basalts erupted from vents in eastern Oregon, eastern Washington, and Idaho. Their eruptions would continue, sometimes furiously and sometimes furtively, for 10 million years. The Columbia River basalts appeared in 4 separate episodes of eruptions. The earliest Columbia River basalts are called the Imnaha basalts. They erupted near the junction of Oregon, Idaho, and Washington. They were not very voluminous and didn't get very far. Neither the Steens Basalt nor the Imnaha basalts appear in the Columbia River Gorge. Things changed drastically about 16.5 million years ago. Huge volumes of basalt, including some of the largest lava flows ever known on Earth, began erupting. In a mere 500,000 years, possibly as short as 250,000 years, a geologic instant, vast eruptions covered most of what is now the Columbia Plateau in hundreds of thick lava flows. These flows are known as the Grand Ronde flows. They're named after exposures along the Grand Ronde River in northeast Oregon. But they're also well exposed in the gorge. Let's take a look at one. Many Grand Ronde flows are really quite thick. They also usually display columnar joints. These columns or columnar joints form as basalt flow cools. The top of the basalt flow is exposed to air and it chills pretty fast. The lava solidifies quickly and it has to contract into relatively small and irregular columns as it solidifies. Geologists call these small upper columns the entablature. They're often curved, but the bottom of the lava flow is somewhat insulated by the ground. It cools and solidifies much more slowly. So, columnar joints can take their time forming. They tend to be larger and more regular. Geologists call this bottom part of the flow with bigger regular columns a colonnade. One way of distinguishing among the very similar Grand Ronde flows is by using their magnetic polarity. Basalt flows contain tiny crystals of iron oxide, the mineral magnetite. As the flow cools and solidifies, these iron oxides align themselves with the Earth's magnetic field like tiny compass needles. But the Earth's magnetic field changes. It even flip-flops. Not the whole planet, just the magnetic field. By taking a very accurately oriented core from the basalt and measuring the orientation of iron oxides in the basalt flow, geologists can correlate lava flows with one another by knowing which were erupted when the field was reversed and which were erupted when the field was normal. We're here in the gorge looking at the Grand Ronde basalts. These thick basalt flows began erupting about 16 million years ago from vents in eastern Oregon, eastern Washington, and parts of Idaho. They're named the Grand Ronde basalts for their deep exposures along the Grand Ronde River. And as you can see here, they're very thick basalts. They're among the greatest of all flood basalts. And these flows extend from eastern Oregon all the way to the Oregon coast, where they form Saddle Mountain, Seal Rocks, and other promontories on Oregon's coast. They're fine-grained basalts, and they contain more silica and iron than many of the other Columbia River basalts. The Grand Ronde basalts, like all basalts, are dark on a really fresh surface, and they're a brown color on a weathered surface due to the oxidation that happens as water encounters all the iron in this rock. The Grand Ronde are typically fine-grained, so let's see exactly how fine-grained they are. So in a Grand Ronde basalt, there's really practically no large crystals that you can see. It's a very dark, plain matrix. And that's one of the things that distinguish these basalts. So that it's very hard to tell one Grand Ronde flow from another. We often have to go to other techniques, chemical analysis, and also using the magnetic stratigraphy, or whether this is a reversed or normally polarized flow, to determine where we are in the Grand Ronde section. About 14.5 million years ago, a new burst of basalts reached the surface. They're called the Wanapum basalts, and they erupted from linear vents in eastern Oregon, eastern Washington, and Idaho. They're really well exposed here at Columbia Hills State Park in Washington. This is the Priest Rapids flow that reached as far as Crown Point. Other flows reached the Pacific Ocean, where they form Haystack Rock and even Yaquina Head. This is the Priest Rapids flow. It kept encountering problems on its way down the Columbia River channel. Its lavas blocked the channel, and then the back part of the flow encountered a lake. When these lavas flowed into the lake, instead of forming columns, they formed round, interesting-looking forms called pillows. Here in the Dalles, we see the bottom of the Priest Rapids flow. You can see the pillows in it where the Columbia River basalts, the Priest Rapid flow, ran into water and as a result chilled into rounded forms called pillows, and ash and explosive chunks of basalt. It's called pelagonite. It's the yellow material around those pillows. Here, the Priest Rapids flow ran into a lake that the front part of the flow created by blocking the Columbia River near Mosier. As the flow entered the lake, it began to fill up the volume of the lake, and gradually the basalt found itself running over not lake water anymore, but solid ground that the basalt itself made. So the basalt then began to cool not as rounded pillows, but as columnar joints. It's much more normal basalt that we see on the top. This is one of the pillows in the Priest Rapids flow. And you can see a lot of diagnostic features of pillow lavas here. For one thing, pillow lavas are rounded. That's why we call them pillow lavas, where they chilled in cold water when they entered the water. Second of all, they have a glassy rim. And this glassy rim is formed as the basalt outside of the basalt chills instantaneously into a glass as it enters this now boiling water. Most pillow lavas or pillow basalts, most pillows, have radial joints that radiate from the center towards the outside, and these form as the lava cools gradually towards the inside. Another real common feature of pillow lavas is this yellow material that's around the outside of the pillow and forms a matrix. This is called pelagonite. Pelagonite is composed of ash from the eruption, ash and small particles of basalt that are broken as the lava chills and then explodes, and sometimes sediment that might be in the lake and certainly in the ocean bottom where the pillow is forming and where all of the steam and turmoil from this eruption churns up some of that lake sediment. Pelagonite is very fragile, and it tends to leave the pillows sticking out of it a bit most of the time, but it's a real characteristic of pillow lavas. We find angular chunks of basalt sometimes in these pillow lavas that are called pepperite. where the basalt never really was fluid enough to make an elongate pillow, but instead exploded, creating a very angular fragment. So pillow lavas are a really distinctive form of basalt, and they're found in the gorge in a number of places. The most stunning example is here in the Dalles, at the bottom of the Priest Rapids flow. We find them also at Crown Point, part of the upper flow at Multnomah Falls, and many other places in the gorge. This is the Rasa flow. It's a massive and very fluid basalt flow, 14.6 million years, that flowed across central Washington and into the Columbia River Gorge at speeds of about 15 miles per hour, according to Kathy Cashman of the University of Washington. It's one of the Wanapum basalts, and it's a basalt flow that's distinguished by having large plagioclase crystals in it, whereas the overlying and underlying flows don't. So let's take a look and see if we can find those large plagioclase crystals. Here they are, and they distinguish the Rasa flow from the Ginkgo flow underneath it and the Priest Rapids flow above it that simply don't have any large crystals, or phenocrysts, visible crystals, as geologists would call them. The Pomona flow is part of the Saddle Mountains basalts. It's 12 million years old. It has thin, what are called Hackley joints, that distinguish it from many other Columbia River basalt units. And that's important because the Pomona flow is the longest basalt flow known on the planet, with one possible exception in India. This lava flow originated near Orofino, Idaho, and it flowed 400 miles to the Pacific Ocean. You see it here at Mosier, and if you go to Astoria and a place called Pack Saddle Mountain and Radar Mountain on the Washington coast, you'll find exactly the same basalt flow. The Pomona flow is a fine-grained flow. It has very few crystals in it, and that also helps distinguish it from other lava flows in the Columbia River basalt group. So the Pomona flow, longest flow on the planet. You can put your hand on it right here at Mosier. By 6 million years ago, the eruptions of Columbia River basalt ended. The last eruptions were mere dribbles compared to the huge volumes of basalt erupted by Grand Ronde and Wanapum flows. But the hotspot that produced the Columbia River basalts is still alive today. We know it as Yellowstone, and it's due to erupt sometime soon. So, the Columbia River Gorge is an important place to learn about the Columbia River basalts. World-class lavas that erupted between 17 and about 6 million years ago. They covered much of the Columbia Plateau with hundreds of basalt lava flows that total 3 miles in thickness beneath Tri-Cities, Washington, and almost a mile in thickness near Dog Mountain in the gorge. They erupted in 4 major pulses, each lasting perhaps 1 million years or more. Of these, the Grand Ronde basalts, 16.5 to more than 15 million years ago, were the most voluminous. In the gorge, they are most accessible up Multnomah Falls. They erupted in northeastern Oregon and flowed all the way to Oregon's coast. Saddle Mountain and parts of Tillamook Head are the distal or far end of the Grand Ronde basalt flows. The Columbia River basalts in all of their forms and all of the flows are one of the true treasures of the Columbia River Gorge. And they're a treasure that scientists and research are teaching us more about every day.